we will be obtaining the equation for reluctance. So you might expect a question. Obtain expression for R, that is reluctance, for toroidal iron ring. For toroidal iron ring. So this might be a question. You will be obtaining a reluctance for reluctance which will be equal to L over mu naught mu R into A. So this is the equation which we are going to derive for this question. Okay. So before we start this derivation, consider a circular. Have you done this? Have you obtained the equation for R? Yes.
No, sir. No, sir.
No, right? Okay, fine. So consider a circular ring, toroidal ring. This is a circular ring at outer surface, and this is inner surface, and this has got a circular coil which is carrying a current I. So this is carrying current I. This will have some area of cross section here. I am just representing an area of cross section. This is A, and you have n number of turns which is carrying current. Because of this, there will be a flux induced inside this toroid. So this dotted lines, what you see is the flux introduced due to this current carrying conductor. So consider a circular toroid of toroidal iron ring having a magnetic path of length L. So here this entire path, it is just like a straight line of length L. You have bent it in a circular form, something like this. So what is this L is equal to? L is equal to 2 pi R. So the length of this coil which is followed by this flux is L. So you have L, which is length of the magnetic path. This phi is the length of the magnetic path, and area of cross section small a, and a coil of n turns, and current carrying conductor, that is current is I. So from the derivation, from the definition in the previous class, Vm, that is magnetomotive force, is given by Vm is equal to Ni, which is equal to line integral, closed line integral H dl. This is from Ampere circuital law from previous chapter. This is magnetomotive force, which is equal to Ni, which is equal to H dl. So can I write this as H into dl, where integral varies from 0 to L, which is equal to HL. Therefore, Ni is equal to H into L, we can obtain H is equal to ampere turns over L. And what is the unit? Ampere turns divided by meters. L is meter and this is ampere turns. This is one equation of magnetic field, but we need to derive the reluctance equation. So the magnetic flux density is given by B is equal to mu H. Remember what we are supposed to derive. Remember this reluctance is equal to L over mu naught mu R into area of cross section. We know that B is equal to mu H, but H is equal to Ni by L. Therefore, I can write it as B is equal to mu. I will represent it in terms of mu naught mu R. H, instead of H, I'll write it as Ni divided by L. Okay, but see, now we can closely relate. I don't have A here in this equation. So in terms of B and A, what should I write? So we know that flux density is equal to B is equal to total flux divided by total area. Therefore, flux is equal to B into A. Therefore, I could write this as flux phi is equal to, what is B? B is equal to this equation, that is mu naught mu R Ni divided by L into A. Right? So I'll just try to reorganize the components here. Maybe I'm just trying to take this component and this component to denominator as L divided by. So phi is equal to Ni divided by L over mu naught mu R into A. Am I audible, guys?
Yes, sir.
Okay, fine. So carefully observe this equation now. So this looks like phi is equal to Ni. What is Ni? Ampere turns. Can I replace this by magnetomotive force? Is this okay? Can I replace this by magnetomotive force? Fast.
Yes, sir.
And divided by L by mu naught mu R into A. Can I equate this as reluctance? Why? Because magnetomotive force Vm is equal to what? Is equal to what? Flux into reluctance. It's just like V is equal to Ri. V is equal to flux into reluctance. So you could see this equation now. This is a term which is related to a magnetomotive force, and now this is a term which is equal to flux, and now flux and magnetomotive force are related in terms of reluctance. How? Because Vm is equal to phi into R. Therefore, R is equal to, that is reluctance is equal to L over mu naught mu R into A. This is ampere turns per Weber. Here also you can see this is magnetomotive force, flux into reluctance. So reluctance is equal to Vm divided by phi. So Vm can be measured in terms of ampere turns and flux is measured in terms of Webers. So ampere turns per Weber is the unit. So this is one equation, very important equation, so that you can directly get some numericals for direct substitution of L, mu R, mu naught is constant, and A or area of cross section will be given to calculate the reluctance. Once you calculate the reluctance, it is easy for us to calculate what flux. If I know reluctance, I can calculate flux. Why? Because Vm will be given. What is Vm is equal to? Vm is equal to Ni. Again, this can be equated to line integral H dl. Is this okay? So I obtained the reluctance equation. So this is, so reluctance equation, I would don't try to write a capital R. Rather, you could write it as an italics R. Italics R. Something like this. Okay. Reluctance, and remember the unit. Unit is ampere turns per Weber. Okay. Any doubt?
No, sir.
Pratap? Pratap is there? Pratap L?
Yes, sir.
You understood this concept?
Yes, sir.
Have you written the notes? So if you remain silent, I'll take it as no. So mark is absent now.
Sir, yes, sir.
Then put it on chat. Just copy,
Okay, sir.
take the screenshot and put it on chat. So I shall start with the second topic of today's session. I'll randomly pick the names and ask you people to post it on the chat box. So make sure that you are trying to note down whatever you understand in the session. So now, since we have obtained the equation for reluctance, I'll write that reluctance equation here. R is equal to L by mu naught mu R A, area of cross section, ampere turns per Weber. I will obtain the expression for reluctance now again for series magnetic circuit. Again, another important question. Series magnetic circuit. So I'll obtain the same reluctance equation. I'll apply this reluctance equation to a series magnetic circuit. Now let us consider the series magnetic circuits made up of various lengths and various material. So I have a material like this. This is of length L1 and this is of length L2 till here. Okay. And here till here it is L2. And I have an air gap. This is L3. Okay. And here you have a current carrying coil of N turns. This is I. Now I'll call this as L1, this length. This is one conductor till here. And this length is another conductor L2. Let me just mark it in a different color. This is L2 and this is L1 and this is L3. And this gap, the length of this gap is LG, air gap. So this is one material, mu R1 with L1. This is another material, mu R3. And this is another material, mu R2. Well, let me just write the permeabilities here, mu R3 and this is of material mu R1 and this is mu R2 and this material is conducted in series including your Lg. This is of mu Rg which is equal to 1 since the gap is considered to be as an air, so mu R value is 1. So if I write an equivalent circuit of this magnetic circuit in terms of an electric equivalent circuit, this appears like this. So this is R3, this is R1 and you have induced EMF here and then you have R2. All are connected in series. This is Rg and this is R2. Well, if I try to blow up this image, you could see very clearly this is L1, length L1, this is L2 and this is L3, length L3. So L1, L2, L3 are the lengths of various magnetic materials used in the circuit. And A1 now here, A1 is the area of cross section of material 1, similarly A2 and A3. So I'll just note those things here. L1, L2, L3 are the lengths of various magnetic material connected in series. Again, LG is the length of the air gap. And now A1, A2, A3 are the area of cross section with respect to that material, and AG is the area of cross section of this air gap. So this is AG. Since L1, L2, L3 are connected in series, I could write the total reluctance So this will create a flux here inside. So let me put it in a different color. So here you could see this is a flux which will be induced due to the current. So this is a flux line. So this is a flux. So the total flux, and obviously if you have the total flux, there will be reluctance which opposes this flux, and that reluctance is again in series. So the total reluctance is equal to R1 reluctance due to material 1 plus reluctance due to material 2 plus 3 plus Rg. That is reluctance due to an air gap also. But what is reluctance equation? R is given by R is equal to L over mu naught mu R A. Therefore, reluctance is given by, I'll substitute for individual reluctance values here. It is L1 by mu naught is constant, but mu R is mu R1 into area of cross section of material 1 plus L2 divided by mu naught mu R2 A2 plus L3 divided by mu naught mu R3 A3 plus Lg divided by mu naught mu Rg Ag. Okay. So now this happens to be the reluctance, total reluctance equation. But MMF, that is magnetomotive force of the circuit, is given by Vm is equal to flux into reluctance. Vm is equal to flux into reluctance. Therefore, I could write it. I'll just multiply this reluctance value with the flux value. So I'll get flux R1 plus flux into R2, because that flux which is generated is constant inside the magnetic circuit, plus flux Rg. So this is now magnetomotive force. So if I substitute all these values here, so what will happen? So it is phi L1 by mu naught mu R1 A1 plus phi L2 by mu naught mu R2 A2 plus phi L3 by mu naught mu R3 A3 Lg by mu naught mu Rg Ag. So this is what? This is Vm. But now if you carefully observe the equation, I have phi by A1 term here in each of the reluctance value. So what is phi by A? Is it density? Is it flux density? B is equal to phi by A. Yes, guys?
Yes, sir.
Okay. So now this happens to be B1 then. So phi by A1 is B1. Phi by A2 is B2. Phi by A3 is B3. And phi by AG is BG. So I'll rewrite that equation again. Since phi by A is equal to V, the magnetomotive force will become B1 by mu naught mu R1 into L1 plus B2 mu naught mu R2 into L2 plus B3 by mu naught mu R3 into L3 plus Bg mu naught mu Rg into Lg. Any doubt? First, you have any doubt now?
No, sir.
Okay, fine. So now if you observe this component, so what is B is equal to? B is equal to mu H, which is equal to mu naught mu R H. Therefore, can I write H is equal to B over mu naught into mu R. So is B by mu naught mu R is equal to H. Therefore, I would write this term as H1, this term as H2, this as H3, and this term as Hg. So what is my final total MMF equation? The total MMF is equal to Vm is equal to H1 L1 plus H2 L2 plus H3 L3 plus Hg Lg. So this is the total MMF equation of a series magnetic circuit. This is ampere turns. Here also you could see H is measured in terms of ampere and length is in terms of turns. Ampere turns. So this is something which is like the current again with the length. Is there any doubts? First, you noted this derivation. So this is the complete derivation for a series magnetic circuit. Let me clear the console. Now you could expect a simple question, something like this, a numerical based on the magnetic circuit. So listen to me carefully. A magnetic circuit employs an air core. That means the medium is air. So if it is air, so mu r value becomes 1. Air core toroid with 500 turns. So n is equal to 500 turns and cross section area of 6 meters square. Cross section area, that is A, equal to 6 centimeter square. 6 centimeter square. So which is equal to 6 into 10 power minus 4 meter square. This is area of cross section and radius of 15 centimeter. So radius is given, radius is equal to rho, which is equal to 15 centimeter, which is equal to 15 into 10 power minus 2 meters. And coil current of 4 amps. So coil current of 4 amps is given, I is equal to 4 ampere. So you need to determine here, I'm writing it here. So you're going to determine reluctance. What is reluctance R? Flux density B, and magnetic field intensity H. And we have the equations for reluctance as L by mu naught mu R into A. We have an equation for B as Is am I audible?
Yes, sir.
Okay, there was a small inconsistency in the internet. How about the screen? Is it visible?
Yes, sir.
Okay, fine. So these are the given data. So these are the given data, and it has been asked to calculate reluctance, flux density, and magnetic field intensity. So R I could calculate using the equation L over mu naught mu R into A. So mu naught mu R and A is given. L is given. So L is given in terms of rho here. I could calculate L also. So L is equal to 2 pi into rho. Because it is a toroid. It's a toroid means what? It is of circular ring and of radius rho. And what is length here of the toroidal ring? L is equal to 2 pi rho. So I know L, I know mu naught is constant 4 pi into 10 power minus 7, and mu R is equal to 1. And A is given 6 into 10 power minus 4. So there's nothing to worry to calculate reluctance. So, but what about B here? B is equal to, we know the relationship between B and flux divided by area of cross section. So what is flux related? Flux is related with respect to your MMF, right? So it is MMF divided by reluctance. But what is MMF equal to? MMF is equal to Ni, right? Ni divided by reluctance. So whatever value you calculate here, you substitute here, and N is 500 and I is 4 amps. And reluctance, whatever value you get from the previous step, you just substitute here, you'll get flux. Once you get flux, you'll calculate what? B, knowing the area of cross section. Once you know B, it's easy to calculate H. Why? Because B is related with H. H is equal to B by mu. So will you calculate by yourself? I will give the answers for reluctance, flux density, and H. So you should get the value for reluctance as 1.25 into 10 power 9 ampere turns per Weber. And for flux, should get 1.6 into 10 power minus 6 Webers, and for B you should get 2.667 into 10 power minus 3 Weber per meter square. And finally, H, that is magnetic field intensity, you should get 2123.4 ampere per meters. So these are the answers. You can take the screenshot of this answer and use this equation, use this set of equation to obtain this answer. Do it as a small homework. Maybe after this session, during your lab hours, you can try to get the solution. Yes or no? Is that fine?
Yes, sir.
Okay.
Yes, sir.
So let me clear this session. Now, this is all about your fourth module. So whatever we have done so far, you could rely upon only on those that particular topic and concept and syllabus as well with respect to exam also. I have left out with few things like reflection concept and standing wave ratio. So these two concepts I have excluded from the discussion in module 4. So maybe if time permits, we shall come back and we shall try to see what is this reflection and different medium and what is the standing wave ratio. We shall quickly go to module 5 so that we could try to get some insights on time varying fields. So whatever we have done so far for module 4, this is more than sufficient. If you could get a concrete, like a confidence on the content or concept what we have dealt, including simple numericals, okay, definitely you can get fetch some good marks over there. So now in module 5, before I start module 5, let me just introduce what is that module 5 and what we are going to cover in module 5. So module 5 is basically a time varying fields and Maxwell's equation. Am I audible, guys?
Yes, sir.
Okay, let me just stop this recording and restart recording. So